I thank the organizers for the invitation, and now let's start. So it's about forcing, and first we will spend quite a time to explain the space of so-called pure conditions. It's like in Matthias forcing, or you have a finite part, so-called stem or trunk, and an infinite part, and those two components together make a condition. And now I need some time to explain this so-called reservoir of pure conditions. The second part is also called pure conditions, and this will be these Ramsey spaces that are named here in the title. So let's start. First we need k-value blocks. If you take k equals 1, then you get exactly the Heinemann space, so the space of blocks. But now I want to have some richer blocks. So k is 1 or larger, a natural number. And a block now, for convenience, has the full support here, the full domain omega, and it goes to the k plus 1, so it has values from 0 to k. And here the support is this finite thing, this shall be finite. And then we go to this fin k set of blocks, of so-called k-valued blocks. It's the function plus 1, and the support is finite. And there's an additional condition that k always must be in the range. This is the analogon to in the Heinemann space, you don't want to have empty blocks. So sometimes I need to read all the different spaces together, and this is this union here. And yes, and now we want to do with sequences of blocks, but we can handle only good sequences, and that they are the ones in so-called block position. So we have two little functions here, and one function is less than the other one, smaller if the support lies entirely before the support of the greater one. So for everybody in the support, smaller than everybody in the support here. And I use finite sequences and infinite unmeshed sequences. They will be the main ingredients of this space here. So either you have a finite sequence of blocks, then M is finite, or M can also be omega. And all my sequences are always in block position, otherwise I can't handle it. And the most important space is the one with the infinite length of the sequences. And there's a little inconsistency in historic notation. We also need the finite sequences, and I took this from Iceworth paper. The finite sequences, they are finally done with squared brackets, and this less here. So the increasing sequences of length 1. So these are our players of the game. So on these blocks we have the partial semigroup operation. I am allowed to add 2 blocks only if they are in unmeshed position here. And then addition is just pointwise addition, and it's the same as concatenation if you see that the blocks live only on their support. Second function, and then infinitely many zeros afterwards. And yes, and now there's a connection between higher k and lower k, and this is the Tetris operation. It goes from fin k to fin k minus 1, and Tetris of a block at an argument is just the value decreased by 1, and you never go below 0. So you could think of such staircases, and now each staircase is just lowered by 1. And some staircases vanish, of course. And yeah. And now we need this, oh yeah, I should, yeah, now let's go on. Now we need an infinite space. So now there is a step in complexity. So, of blocks. It can be meshed or weird or anything, but there is one condition, it's min unbounded. I didn't write this down. This means that it at least contains one block that starts after n for each natural number n. I don't want too little reservoirs yeah, or too weird reservoirs. So the bad thing that's forbidden now is a set B that would be with staircases that all start before a certain n. That's forbidden. I want for each n some staircase in my set B that starts only after n. That's min unbounded. And yeah, a staircase is a good picture for a block because we will have a partial order on the blocks that says that the blocks of this neat shape, they are dense. So you could always do with such things that first grow to K and then they go down again. And even you can require that there are no gaps, that each step is taken, so no jumps. And so this is a nice picture for a block, and this picture is actually very useful. And now we combine infinitely many blocks here. We have a set of blocks and we take the Tetris finite union closure with respect to K of this set. And this is, in Stevo's book, it's called the generated semigroup. And this is the important object for coloring. So we take finitely many blocks here, L plus 1 many, in block position. We are allowed to lower each block by some iterated application of the Tetris operation, J 0 times to B n 0, J n L times to B n L, with a side condition here that one guy must be unaltered. So in one position here, the Tetris operation is just a zero application, so nothing. That means at least at one place we reach the full height of the staircase, so that K is still attained for each of these in each of these little sums. This is guaranteed here by this condition. And otherwise, there are arbitrary lengths and arbitrary combinations of exponents here. This is the partial generated subgroup. You would, of course, ask, why do I need to be so complicated? Why not just addition? Why this Tetris operation is used at all? But this is a phenomenon, the Gauss coloring works only if you do with a Tetris operation. The Heinemann is the special one between 0 and 1, and there the Tetris operation is not visible, it just means dropping blocks. So yeah. And a closed set is one which whose generated semigroup is just the set itself. That is a TFUK set. And I also use it not only for min unbounded sets, but also for these sequences we had on the former slides, the unmeshed sequences. And here just I identify the sequence with its range. And because it's an unmeshed sequence here, since it's an unmeshed, it's min unbounded. And yeah, so now this partial order, where I advertised already that the staircases will come out as a dense subset. So yeah, this is the condensation order. So yeah, Oh yeah, there are a lot of is missing. Oh yeah. Oh, sorry, I botched somehow with the tech. So there should be 2 of them, and I must write it on the blackboard when somebody is smaller. And let's stick to the alphabetic convention. Say he is smaller or stronger. Will be also stronger in the forcing. If it's a combination, if he is in here, if the range of B is a subset of TFUK of A, and of course B must be unmeshed. So this is a short way. I'm sorry, this is somehow left out from the slide, but this is a short way to write it, but you can also see it more like a procedure, what you do. You are given A and you look for a stronger B. What do? You have the A here, which is an infinite sequence of staircases. Then the first decision is about blocking, about this N0 to NL all the time. So say this one, then the next one. Then within each block, we have to decide for one which is preserved in the full height, and for all others we are allowed to lower in as many iterations of the Tetris operation as we want. So this is the condensation order, and the outcome of the condensation is the stronger one. And for managing the space, for getting a Ramsey space, I need to work with approximations that work fairly well. And this approximation by indexing this A by A0, A1, and so on, this is not a good one, because by condensation then B0, which is a condensation of the A's, could be arbitrarily far out, and so place 0 wouldn't mean any boundedness. And so I take absolute places, and this is here going with the supports. The supports lie in the natural numbers, and so I am given a sequence and I should look for an appropriate tail, and here it's by indexing by just a finite piece, and A past P is then just the parts of A whose support lies entirely after the support of P. So here it's playing with the natural numbers and not with the indexing. So here I would say, if I try to do some diagonal construction, to do some very good object, I would say, well, first let's freeze this, and this is the tail. Then in the next step, let's freeze this, and this is the tail, and so on. So this is this past operation. So yeah, and this condensation order has a funny phenomenon. I don't get any use out of it. It just says here, if 2 conditions are compatible, then there's even a weakest one witnessing the compatibility. I don't see any benefit of this for the Ramsey space, but what's used in the forcing is that this witness for compatibility is gotten in a very computable way by saying here, we look always for the smallest piece witnessing compatibility and go on piece by piece. And smallest now means we put a lexicographic order on the blocks. And this is quite arbitrary. I chose for an order of order type omega. So 2 blocks are in this lexicographic order, of course, first if the supports lie in the order. And in same support, I take the weaker one as the smaller one. So this is weird here, this is smaller because it has a larger value, so it's weaker. Because with the Tetris operation, you can still lower the value. And then we go on like this here, and if we know they are compatible, we can take the minimum here in the lexicographic order, about here witnessing that it's an initial segment of the stronger sequence of both of them, and then go on like this all the time, iterative. This will be used in forcing. If you need to force a name and want to pin it down, the thing to do it is by finite approximations. But otherwise, there is a question for experts in Ramsey theory, whether these Ramsey spaces where compatibility is witnessed by a weakest witness, whether this would help somehow. In the Blas-Schellach space, for example, this is not the case, but I do not see any difference in forcing. So yeah. So now for heading to a new forcing order, we need to restrict our space, phi k to omega, to some smaller space, which is not centered, but somehow centered in its projection to omega. And yeah, so now we need to fix parameters. And the parameters are indexed by our k, the values here, and another index, a second, which is minimum or maximum. And for each, the minimum, which one we would like to fix the minima of the staircases, and the maximum set, they might be empty. Then it gets just back to the full space. You can also take just the full set, but then you get always an even number to the k, 2k many parameters. And for each parameter, we fix a Ramsey ultrafilter over omega. And they shall be pairwise, not nearly coherent. This will be on the next slide, so I will explain this. So somewhat, for Ramsey ultrafilters, you can also say just not isomorphic, non-isomorphic Ramsey ultrafilters. For my applications, I use here Ramsey ultrafilters, but you could also use just selective co-ideals. That would suffice to do the Ramsey theoretic machinery. So this is the space now here. I have fixed parameters, and sometimes I want to fix only an end segment of the parameter, and for technical reasons I fix the end segment here, not the initial segment, but the end segment here. So if I restrict, the restriction is on the I part, and the X part is not affected, the minima and the maxima. And now the space, the subspace of phi k to the omega, which will be the reservoir of a new forcing order. So I call it phi k to the omega, indexed by bar r. This is the sequence of non-nearly coherent Ramsey ultrafilters. And so these are the block sequences that have these three additional conditions. So for everybody from the minimum indexes, the rims of the staircases shall be in this ultrafilter. So you have an infinite sequence, and so you get an infinite set by saying here, for example, here R1 minimum. We look at this point, and then at this point, and this point, and so on, and we get an infinite set, and this infinite set shall be big. It's in the ultrafilter. And the same for the other values. So the value is always I here, and I was very picky. I take pre-images of singletons and then a minimum or the maximum, and the n runs, this is over all the blocks in the sequence. This gives infinite sets, and the two infinite sets here shall be in the respective ultrafilter. And now I put, for convenience, to have my space a bit smaller, I take here only these ordered staircases. So the ones that fit to my picture here, always climbing up with no jumps and going down again. And in case some parameters are left out, then you have jumps, but otherwise not. I always take this order, maybe with some thinned out conditions here. Yeah, so this is the space now. And you could think of the full fin K, but here only sequences that respect some fatness condition here. If I drop too many from my sequence, I get out of the ultrafilter. So yeah, but now I shall explain also the near coherence. This comes as a necessary requirement from old work by Puritz. If you want to learn about it, you should, I recommend the paper by Blas on ultrafilters related to Heinemann's theorem. There it's explained why you, if you want to build an ultrafilter, say on the product omega to omega with fixed projections, there's a unique possibility only if you fix minima and maxima and have non-near coherence. In the case of near coherence, you would get a third ultrafilter on the diagonal, and we don't want to have it. That would spoil our space here. Somehow the space needs to be sufficiently fixed by knowing only its projections. And I mean now with projections, this information about the rims of the staircase. So I know the rims of the staircase, and this gives me some information about the full sequence, but not the whole. And yeah, so now near coherence. Two ultrafilters over omega, we say R is nearly coherent to S. If there's a finite to one function that after this, and this mapping is going in this way, F of an ultrafilter are the subsets of omega whose pre-image is in the ultrafilter. So it's like the Kiesler order, but here I do with a finer order, it's finite to one functions. You would get a very good notion for forcing also if you do any function here. This also gives already a connection between ultrafilters. So yeah, and but we often now want to do the negation of this. And on the ultrafilters, this is a near coherence, is an equivalence relation. And yeah, there would be one class of the principal ultrafilter. We leave this out. We use only non-principal ultrafilters. And if you have an ultrafilter, then this F image is also ultra. The reverse does not hold, but the difference is slight. So yeah. Doesn't matter for us here because we work only with ultrafilters. Yeah, and yeah, for technical reasons, because I don't have only centered sets, I need to find the generalization of the negation of this notion here for arbitrary subsets of omega. We do it now for co-ideals, and here is the negation of this definition in a slightly different, slightly generalized context. So we now have families of infinite subsets of omega. So say closed upwards under supersets, that would be enough, but you can also have a co-ideal. Does everybody know what is a co-ideal? So that is the right thing to do combinatorics here. So one is not nearly coherent to another if for every finite to one function, so this is just here there is, then for all. But now I need all locations because it's not centered. I say for each starting point, x0 in A0, x1 in A1, H1, there is a stronger one, a smaller one, such that their images are empty. So this is just that two of them can't be in the same ultrafilter. So yeah. So now we did this localized space. You probably know localizations of this fin-K to omega space. The famous one for K equals 1 is the so-called Millikan-Taylor ultrafilter, or also the equivalent name is stable ordered union ultrafilter. That would be a centered subspace of the full space fin 1 to the omega. That would give a sigma, have a center. We can do this. We can take a centered subspaces of this fin K omega, and then we get generalized Millikan-Taylor ultrafilters. We have to worry whether we want to have some condition accommodating the Tetris operation, and this can be done, and then we get the analoga for the stable ordered union ultrafilters on this space fin K. But now I don't want to go so far and cut my space down to a centered space. That's too poor a forcing. So in this space here, we really have still incompatible elements. So if you only put here the rims of the staircases, you don't get yet the full information about whether the two of them are compatible. This is a bit playing with ultrafilter situation. You would now think here, if I fix all the rims of the staircase, I have fixed everybody, but I'm dealing with a full set of members of the ultrafilter, and so one can play a bit here. This is still a space that is not just an ultrafilter over this space here. Yeah. Okay, and now we need that this gives a good Ramsey space. And for Ramsey spaces, you usually have a coloring property. You color finite objects, and you want to find an infinite object so that it's monochromatic. And this theorem, which has quite a long proof, is an amalgamation of two cases that were previously known. The special case of value 1 and minimum and maximum fixed is in this paper I already recommended. And the case with nobody fixed and K equals 1 is the Heineman's theorem. And the case with no parameters but arbitrary K and the Tetris operation accommodated, this is Gauer's theorem, where he solved something about Banach spaces. So let's read the theorem. We fixed our parameters. We have a sequence in our space and the coloring of the blocks here. The blocks that are stronger coming from in the generated semigroup of this sequence. And then there is a stronger block sequence such that its generated sub-semigroup is monochromatic. Yeah. There are now two slides about some ingredients of the proof. A proof goes via the Galvin-Glaser technique. There's a even the easier question to prove the original Gauer's theorem, so without parameters. In the Baumgartner technique or without ultrafilters, long ago. It's for K equals 1, it works, but the increasing K and accommodating the Tetris operation has not been achieved without going to this ultrafilter space. So yeah, first of all, for getting a Ramsey space, we need a diagonal lower bounds to do some construction by approximation. And here, for technical reasons, I need a bit stronger notion of diagonal lower bound. suppose we have a decreasing sequence here. So a sequence of sequences here. So here's the bar. Each of them is by itself a sequence of blocks, and they decrease in n. So they get stronger and stronger. And I want that the bound doesn't vanish. Still a good lower bound would be a diagonal lower bound, where I know the mistakes, so it's an almost bound. In the almost ordering, finitely many bits might be wrong, and such guy B is called a diagonal lower bound if for each block in B, the B after the block lies is stronger than the C that's indexed by the maximum of this block. Plus one or does not, or not plus one, this does not make a difference. This is Ainsworth tradition. Matthias tradition would be without the plus one. So don't worry that there are various notations of diagonal lower bounds. And also, there are even pairwise incompatible diagonal lower bounds. So it's a very vague notation. You just have a sufficient description, but it's not any computational one. But here I want even some more requirement here, that the parts here, that they are not gotten by semi-group operation, but they are just taken by some original. This is not important because we won't see now into the proof. It's used in some so-called Grigoriev argument in the end, because my space requires fat sequences, and for getting fatness I need to therefore this technical for experts here. And this is the one with the Galvin-Glaser technique. It's the only thing to my knowledge the only technique to prove Gauer's theorem, and also this theorem we do with ultrafilters. And now we do even with ultrafilters that respect the projections here. So if you take all minima of the staircases in the ultrafilter here, you would get here just the R, or at least the subset of R. So you take here idempotent ultrafilters on this space here. So it's ultrafilters if you just think of the ground space is the set of finite blocks, and you have an infinite set of blocks, and it must be measured in or out. But then it's not beta, as is usually used for ultrafilters. It's called gamma here. These are the min unbounded ultrafilters. You must have ultrafilters that have sequences arbitrary late. And then you do such a machinery here with a row of projections. I won't go into it, time is short. And so in the end you are interested only in UK, which is the one on the full space, but for accommodating the Tetris operation you need to have these end segments. And there is of course, there is a difficult computation with the indices, because RK rules who is the pre-image of K. But once you do the Tetris operation, it's the pre-image of K minus 1 and so on. And therefore it's this weird indexing by the end. Yeah, and finally we get to this was the end of the sketch of the proof of this coloring theorem, and now by the known stepping up technique by Millikan and Taylor, you can do now an n-dimensional coloring. So instead of coloring just the one TFU of A, I color pairs or n tuples in increasing order, so a much richer coloring, and still I find the monochromatic condensation here. And so this is used for evaluating the forcing, it's very convenient to have this, that you have one condition who does a lot of jobs then. So yeah, and now we are ready to define a notion of forcing. Now comes the finite part. So we have now worked a lot on the infinite part, and now we take here, well, this is a made-up name. I said Gauss-Maté forcing with parameters R bar. So Maté forcing often is done with this M, and K indicates the dimension, and here the R bar. So its conditions are pairs. The first part is the block, and the second part is a sequence of our parameterized space. And the block lies before the beginning of the sequence. And the forcing order is the block is lengthened in the stronger condition by a part which is gotten from the reservoir, and here's this plus, but by this plus, of course, all the bounds will vanish. You won't see S and from S bar. It's just one block after this operation. So it has big amnesty about the blocking, otherwise we would add a dominating real, and we don't want to do this. And well, and the reservoir is just strengthened here, and it's of course taken only after the part who is used here. So this is a forcing order, and we have to worry whether it's a benign forcing order, and benign would be proper here.
So you're not requiring just that T is a subset of T if you be concatenated with A. You want necessarily to have at least one more point where you can K?
Yes. That's important. Yeah. Because my generic must attain K infinitely often. Yeah. Good. Okay. And we have we can define axiom A ordering, but this is useless if it's not good. And the good thing is the pure decision property. If we have a decision, yes or no decision, or a decision between finitely many options, and the condition, then there is a pure extension. This is called pure. You don't lengthen the trunk here that decides it. And this is just the translation of the coloring theorem we had 2 slides ago. And so we have a proper forcing. From this you get, by known techniques, you get proper. So yeah. So this was now done for this full space here. Now for going into iteration, I need also subspaces of this one. Now let's axiomatize what we used for goodness here. So instead of taking this here, we take an abstract one and list what we used for our proofs. And the listing is the lower bounds and the Gauss property and closed under weaker conditions. An equivalent formulation would be here in number 2 to have diagonal lower bounds. This is gotten for free. If you have 3 and 2, you get this stronger form of 2. So you can do with either one. And also you get an equivalent definition if you take here the n-dimensional one, the stepped up coloring theorem. This is also gotten for free here. So examples are the full space, then the one which I already had here, this Millikan-Taylor ultrafilter, and the R will be just its projection, and I equals 1. This was the known case here. This is also on this Blas paper. If you take a stable ordered union ultrafilter, its minimum and its maximum projection are non-nearly coherent Ramsey ultrafilters. Then you can do this generalized thing here, Gauss-Millikan-Taylor ultrafilter, which is like a stable ordered union ultrafilter, but the generators are closed under the Tetris operation. And then, not under the Tetris, under the TFUK generation, you don't want to lower. And Then, yeah, there's an entirely different space, but the abstract for this talk was required so early, so I cannot talk about this different space. This was my work in the summer. So we could also do with power sets of the power set in the Blas-Scheller creatures instead of these Millikan-Taylor creatures here. And yeah. So then some similar phenomenon shows up. And yeah, so now let's go with forcing. Now we have this notion of forcing, mk of h, and we take the generic real. First we take a very modest one. We take just, yeah, the union of the stem. But it's a very good one because it now gives k values here. So it's like k infinite subsets of omega. So these, and actually really I want to name the fibers. First of all, the name for this is just the natural name here. We take just here the stem and then the condition, and then here anybody here. And if you evaluate this with the generic filter, you get this here. And from now on I will identify names and objects. Okay, oh thank you. And so we take the fibers. These are these pre-images of each of them. So they are infinite sets. They are now much, much thicker than the staircases. So let's compute the fiber here. So this would be here this one, this one, this one, this one, and so on. So this is, yeah. And yeah, so these fibers, they are bad guys. They are not measured anymore, and yeah, they are out of the foreign ones, but the ith fiber destroys this one. This is just a generalization of Blas work. The minimum and the maximum projection get destroyed by forcing. And we have also a very slow generic function, which is just counting when the next guy comes into the support. This will be our generic finite to one function. And now we need to evaluate the forcing. I skip this slide. We only have 5 minutes. You don't want to go into technique. This is a pure positive density argument, nothing with preservation. So just evaluate it, and we take the fruits of it. The fruit is that the p-point in the ground model will be preserved if it's not related to the fixed Ramsey ultrafilters here. Oh yeah, this is not root in Blas below. This is in our case, since we have ultrafilters on both sides, it's equivalent to non-near coherence. So for a foreign p-point is preserved by our forcing, and all others are identified. Now I take 2 foreign p-points, and this was the second part of the technical lemma, and it says that my generic very flat function identifies each surviving p-point. It applies only for p-points, otherwise we don't, other ultrafilters might be destroyed. So, and now we start to iterate. Now we have this filter here, it's destroyed, but it's not measured. This means this guy is positive with respect to this ultrafilter. So it's intersected with this generic guy is infinite. So I have a candidate for a filter base to extend it to next one, and to show that this can be extended again. And so we take the positive sets here. So the filter generated by this and the positive sets, we had it already in plus minus yeah, selective co-ideal or happy family, and it avoids the E. It's not nearly coherent to this one p-point preserved, and even the members are pairwise not nearly coherent in this generalized notion. And then I can do Mathias's apparatus under CH. We can even construct the next extension, which is Ramsey. And there's another step of the proof we skip. This is pure computation with names here. I propose a name for the lower bound, and thanks to the Millikan-Taylor coloring theorem, I know enough about the name. And then we start an induction and go on in this way all the time. So we take the ultrafilter, destroy it, take the next one, and all the time so on. So, and we go by countable support, by induction. In each model, we define the next ultrafilter sequence and go on and preserve one. And this last part is gotten for free by a CFC phenomenon. This is a generalization of a theorem by Blas and Banach, where they solved the number of near coherence classes. And there is a funny CFC phenomenon about small test cases. Yeah, and so that is the outcome, that in the end we have these growing ultrafilters. We have one preserved one in the ground model, and so many parameters we fixed, so many Ramsey ultrafilters we have. And another CFC consideration says that these are all ultrafilters, all near coherence classes in this model here. So, and yeah, that was the main result, and one can also see it as a factorization and ask about this. What I worked very much last fall, and was my talk in Lumini about the forcing with these Millikan-Taylor ultrafilters. They also show up in our construction, but only at the intermediate stages. And then they vanish again, because you can factorize it and this gets destroyed, and they really vanish. This is the last result here. In the final extension, there is no stable ordered union ultrafilter, and also no general bigger than. Read just k prime equals 1, then you have a stable ordered union ultrafilter. And this is the case because there's a proof even it would reflect down, but since we have only finitely many classes in the model, also this would reflect down. So at an omega-1 club of stages, you had two contradictory situations, and this can't be. So this is an old conjecture by Blas that two non-isomorphic ultrafilters do not imply the existence of a Millikan-Taylor ultrafilter. So this is here, you take here PP at least 2, then you get two non-isomorphic ultrafilters. Well, and that's it. Thank you very much.